Hi, Jeff Disher here again. Today I'm going to talk about something which will be a little on the technical side, but I'll try and kind of keep it nailed down to things that are concrete, because this is kind of leads up to some things I want to talk about later. So today is going to be all about memory management. So what is memory management? What am I talking about here, and why does this matter, and what does it mean in terms of how software actually works? Well, whenever a program running on a computer does pretty much anything, it's doing this within a piece of memory. So this, of course, meaning like sticks of RAM within your machine, not hard drive storage space or anything like that. That's different memory. So this is what the program actually uses to store intermediate values or information that it's reading in or about to write out. And it uses this memory that it's allocated to perform the operation that it needs to do to actually fulfill its purpose. So what's memory management though? Why is this a thing? It just sounds like, okay, you get memory and you use it. Well, there's different ways of thinking about how memory actually works, and it kind of depends on how your program itself needs to actually accomplish its task. So I'm going to go over sort of three main ways that this is considered, and this is going to be from sort of a perspective of something like a C program, but it's going to be very common across many different programming languages. And it's also not something specific to the implementation. I'm going to try and keep this more about how the program needs to try and do its work. So the first one of these things is what happens when you've got a program that says, okay, every time you run this program, it needs a certain amount of memory, like 1 megabyte or something, and it always needs a megabyte because that's how big this piece of information is that it operates on, maybe. So no matter what it's doing, no matter how much work it's actually doing, every time you run it, it always needs that amount. So this is a constant amount of memory no matter what it's doing, no matter how long it's running, how big its input data is, or anything like that. This is actually a very common phenomenon too. Most programs are like this. They need relatively little memory. It's usually something you can determine right away. You know when you're writing this exactly how much it's going to need to accomplish its task. So this is what we end up calling static allocation. Now this is because the amount of memory you use is fixed. It is static. It is known at compile time when you first write the software. You know exactly how much memory it'll need. And many programs use this. But then again, this is many very small programs, like a lot of the little utilities you'd have on your computer to perform certain little operations, listing files, things like that. Like a lot of little simple things. These can usually be written this way. But as things get more complicated, as we'll talk about going forward, it gets further than that into some more complicated areas of how to look at it. So the next way that kind of a program thinks about how much memory it needs is maybe it'll be something like, okay, well, every time the program itself tries to perform a certain operation, like maybe it's trying to read in some data and, I don't know, decrypt it or something, maybe it'll say, okay, well, every time I do this, I always operate on a certain amount of memory. So every time you call into this part of the program to do something, it needs that much memory. But it only needs it when you get in there. But also, if you're using that part of the program in many different places or at many different times, each time you call into it, you need that much memory. Now in this case, what we do is something called a stack allocate. So this way, because the way the program runs is every time you call into a function, it creates a stack frame. This piece of memory, as I talked about in some other videos, this piece of memory that it operates on within that function itself. And when it's done, it discards that. Now this is something which is fairly easy to contain as well. The actual overhead of doing that allocation for the stack frame is very fast. There's a limit to how much that can be, but usually you can determine what that limit is when you're writing the software as well. So this allows a certain kind of versatility in terms of how it's actually running, but it's not actually going to really change anything in different ways while the program's running. You can kind of, okay, yes, it might need more as it goes, but it's going to need it more subject to these kinds of limitations based on what it's actually doing. Now that brings us to the third type of memory allocation and management that I want to talk about, and this is dynamic allocation. This is when you can't constrain anything at compile time. You have no idea what's going to be happening. And there's many, many reasons why this could happen. Maybe it's something like, oh, we need to give you this data file, but you don't know how big the data file is. You just have to find out when you're running and say, okay, well, we need to allocate a bunch of memory to put that in there, and then use that and then give back the memory later on. Because the thing is, in those other cases we've talked about, How you ask for memory and how you give it back were kind of automatic. When it's static, you get the memory once, and you never really give it back until the program terminates. And that's fine. So you don't really have to do anything. The OS will do the cleanup for you and the setup and allocation for you. So that's nice. In the stack allocation case, that was something where you'd allocate the memory just when you called the function. This would happen kind of as a side effect of you calling it. You didn't really have to do anything special. And when you returned from the function, when you finished that little algorithm you were running, that would give back your stack frame, which includes the memory allocated. So that all happens for you for free, automatically. You didn't really have to do anything. But in this case, it's much more complicated. Now we have things like, okay, I asked for memory, now I need to remember to give it back. And this is what leads to many sort of complicated issues within how software actually works. And it's when you get things like, if you've ever heard of someone talk about a memory leak. Usually that's when you asked for memory and then you forgot to give it back. And it leaked, which means that now it's just memory that your program is wasting, but it's not using it because it forgot about it. It forgot to tell the operating system, you can have this back now, I'm done with it. And the operating system can't, in general, determine that you were done with that unless you told it that you were done with that. Now there's certain kinds of programs that can do that, which we'll talk about in a future talk, which is all about garbage collectors, as you might see in things like Java, which don't have this problem, but they kind of look at it a different way and they manage some of that for you. But in terms of how a lot of direct programs work that actually take direct control over how they use the memory, they have to make sure they give it back. Now, just one of the last things I want to touch on related to this, because the issue of how you actually manage memory and how you make sure you give things back and that you don't leak and that you're only asking for the right amount at the right time, that's a very complicated area, and it really has a lot to do with the actual context itself of specifically how you're writing the software or what exactly it's doing within a situation. But one of the things that is worth talking about broadly about all these is certain performance implications. Now, the way to look at this is, remember, memory, it's something that it's far away from your CPU. It actually takes time to get to it. But the CPU can actually cache, it has what's called the cache, which can cache the memory that you're accessing. Now this works really well, assuming that it can cache the memory. So that means things like it'll cache things you've used recently or things that are close to things you've used recently. So this is what we call temporal or physical locality. And these are important because they actually matter a lot to CPU performance and overall application throughput. And in fact, it matters more and more over time, which is kind of interesting. But the better you are at this, the more true it seems to become. So it's valuable to understand that. But this is something that where there's really a lot of differences in terms of how these different ways of looking at the problem actually work within that environment. The obvious one is the static case, where you're allocating only everything up front. Well, the system could make sure that that memory is just close to wherever you're running, so that it'll always be really closely localized. It can make sure that all that memory you're talking about is really, really close together, because it knows exactly how much there is. It doesn't need to put space between them for making sure you might need to get something later. Nothing like that has to happen. So it can actually pack this together really nicely, and it can put it in exactly where you need it to be. So this can actually be, it's usually very, very fast to access static memory that way, because it works really well with your cache. Even if you're running across multiple CPUs, often some of this can be done for you that way in a very transparent way as well. So assuming that that matters in a multi-threaded program. So that usually works very well. In the stack allocated case, this usually works well too, because that stack is also very well packed. Now there's other things on it that kind of get in the way, and that can become a bit of a problem. But generally speaking, these things are all really close together. Also, the way the stack works, it's always right next to where you're actually running, which is really nice because it means that that memory is typically very, very hot for your CPU. It's really close to you. It's really close to you. It's usually in your cache already because you keep reusing it. So usually stack allocation is also really, really fast. Now the problem is when you look at things like the dynamic allocation case. In this case, the memory is often far away, and also there's often space in between it. If you do a bunch of different dynamic allocates one after another, they're not going to be right next to each other. They're going to be kind of spread out because that system that dynamically gives you memory, it tries to make sure that, okay, well, what about in the future if you ask for more memory, but I can kind of fit it between some of these other ones you just asked for. So it kind of tries to spread things out a little in order to avoid certain kind of waste scenarios that are actually fairly common. So because it needs to worry about that waste, the amount of space in between things. So in that case, you often end up with sort of a slower access to memory, unless of course you keep using the same thing. Then it'll become temporally localized for what your algorithm is doing. So anyway, that's sort of a very, very quick look through a bunch of different concerns relating to memory management. And it's something that I want to kind of use this as the basis for in a future talk, talking about how garbage collection works, some concerns related to that, why it's probably better than you think it is, things like that. Because that's valuable, and it's something that you do see come up a lot where people are talking about performance in Java, Python, something like that, different languages that actually do this for you, and they're worried a lot about things like garbage collection. They usually don't need to be. Usually they need to worry about something else. So we'll talk about that in a future talk. As always, like this if you thought it was informative. Leave a comment below if you have any questions, or of course contact me directly if you have any questions as well. Thanks. Bye.